In the architecture of a high-electron mobility transistor, the most critical electrical activity often happens right at the boundary. Historically, engineering approaches treat the top layer of silicon nitride, or Si3N4, as a simple sealant. It is applied to mitigate electron traps at the surface and stabilize the overall device. But treating this layer as a static, protective shell ignores its true physical influence. Modifying the nanoscale thickness of silicon nitride actively alters the charge dynamics of the two-dimensional electron gas, or 2DEG. Changing this initiates a competition. Electrical trapping captures electrons at the surface, while the material's physical presence applies mechanical strain, pulling on the underlying crystal lattice. Tuning the performance of a heterojunction device requires mastering the precise mathematical balance between these two forces, rather than simply applying a thick coat of dielectric and walking away. To measure exactly how these forces interact, we can analyze the performance of devices across four highly specific silicon nitride thickness variables: 0, 20, 50, and 120 nanometers. Measuring the top layer in isolation presents an incomplete picture. The electrical response of the entire system depends heavily on the architecture of the underlying epilayers. We can observe this by testing two distinct frameworks. The first is a standard heterojunction built with an aluminum gallium nitride barrier over an aluminum nitride interlayer and a thick gallium nitride buffer. The second test structure uses an identical base, but adds a very thin 2-nanometer gallium nitride cap right at the surface. By tracking the nonlinear relationship between the silicon nitride thickness and these two structural variations, we can isolate exactly how passivation modulates carrier density and leakage current. The first step in isolating these variables is to examine the device's current voltage profile, paying particular attention to the reverse bias leakage current. Researchers took temperature-dependent measurements spanning a wide thermal range from 100 Kelvin up to 400 Kelvin. This line graph illustrates the results across that entire thermal spectrum. Notice that in the negative voltage range, the reverse bias currents are tightly grouped, exhibiting almost zero temperature dependence. If thermionic emission drove the leakage, currents would scale aggressively with heat. The flat response eliminates this. Instead, tunneling conduction governs the leakage. Further evidence is in the forward bias region, where a slight kink appears, a signature of low bias tunneling. While total leakage current shifts depending on the silicon nitride thickness, the data reveals no linear, predictable correlation between them. Since this relationship is nonlinear and dominated by tunneling, leakage variations cannot be explained by thickness alone. We must look at the specific charge mechanisms occurring at the surface. This equation represents the strict charge balance governing the two-dimensional electron gas. Here, donor-like surface states act as an electron reservoir. Those electrons drop down into lower energy states to populate the channel below. Applying a silicon nitride passivation layer neutralizes a significant portion of these surface donor states. Removing this primary source of electrons should theoretically reduce the total carrier density. But a competing mechanism forces the math backward. Thicker silicon nitride introduces significant tensile stress to the lattice.
This physical stretching generates a localized positive electrical field. To maintain overall charge balance, this positive field draws additional electrons from the environment down into the 2DGE. The final channel density is the strict net result of this tug-of-war, trap neutralization stripping electrons away, while tensile strain forcefully pulls them back. We can prove this physical strain and trap model empirically using capacitance voltage, or CV, profiling, measured at 100 MHz. This capacitance voltage chart isolates the left cluster of curves, representing the bare aluminum nitride interlayer structure. Notice the distinct monotonic decrease in maximum saturation capacitance as silicon nitride thickness scales up from 0 to 120 nanometers. To understand why this drop occurs, we define the total capacitance of the system mathematically as a series connection between the layers. The total capacitance equals the capacitance of the passivation layer multiplied by the capacitance of the barrier, divided by their sum. A lower total capacitance physically indicates that as the passivation gets thicker, fewer electrons are available to saturate the channel compared to an unpassivated sample. The surface states have been successfully neutralized. If we apply a high negative bias to the gate, the electrons are pulled out of the space charge region. The depletion width expands infinitely large until the 2DGE channel is completely choked off. The point at which these capacitance curves drop to zero exactly matches this physical pinch-off, confirming that the thickness of the surface layer directly dictates the availability of charge deep within the device. If we shift our focus to the second test architecture, the one capped with a thin layer of gallium nitride, we must ask how this physical addition alters the series capacitance model. The gallium nitride cap introduces a third capacitor into the series calculation, effectively functioning as a physical spacer between the passivation and the barrier layer. This graph plots Hall carrier density against silicon nitride thickness, revealing two distinct behavioral tracks. For the gallium nitride capped structure, carrier density climbs initially, then abruptly plateaus at exactly 50 nanometers of passivation. The bare aluminum nitride structure behaves entirely differently. Without that physical spacer, its carrier density continues a steep upward climb, requiring a full 120 nanometers of silicon nitride before finally hitting its saturation point. The underlying epilayer design physically dictates passivation limits. The cap creates an artificial bottleneck, arresting charge transfer far earlier than a bare surface. Zooming out, these mechanisms present strict rules for the physical engineering of high electron mobility transistors. The first principle is that passivation is a highly active variable. It directly modulates the 2GD by serving simultaneously as a trap neutralizer and a strain generator. The second principle is that tunneling leakage is inextricably linked to this precise balance of surface charges, rather than to ambient temperature. Finally, adding architectural spacer elements like a gallium nitride cap physically restricts the threshold for carrier saturation. Modifying the thickness of a silicon nitride layer in isolation will not yield predictable results. True device optimization requires treating the top dielectric and the underlying epilayers as a single, interdependent electrical system.